Well, hello everybody. My name is Doug Frey, and welcome to my YouTube video tutorial having to do with COMSOL Multiphysics. So again, my name is Doug Frey. I'm at the Department of Chemical, Biochemical, and Environmental Engineering at the University of Maryland, Baltimore County, UMBC. And this is my COMSOL Multiphysics tutorial, sort of a beginning tutorial, and it's focused on COMSOL version 5.2. And this is part 1 of this tutorial. This tutorial is part of my transport phenomena course. And this course, let me check something here quickly. Make sure we're recording. Yes, we are recording. Okay. This course is, so the Transport Phenomena course, ENCH 630 at the University of Maryland, Baltimore County. I have a complete website that is focused on this course, and if you just Google Doug Frey Transport Phenomena, you'll come to my course website. So as I mentioned, this is a tutorial on COMSOL Multiphysics. And in my transport phenomena course, I do introduce students to COMSOL Multiphysics. And currently in my course, we're on problem set 2. And problem set 2 involves 4 problems, three of which are from Bird, Stewart, and Lightfoot. So BSL stands for Bird, Stewart, and Lightfoot, and they all have to do with flow in cylindrical geometry, either in the axial direction through an annulus, in the theta direction, in the gap between, or in an annular gap between two cylinders, or in the radial direction in cylindrical coordinates. That's those first 3 problems. And the 4th problem, again, cylindrical geometry, but it has to do with the entrance length or laminar flow in a cylinder. I'm going to put this problem statement on my website so you can read through it. But in a nutshell, I can explain the idea of this problem set. And again, the idea is entrance length in a tube. So let me change the color here back to red and the line thickness back to medium. So entrance length in a tube, so we have sort of a bulk fluid out here, and it's going into a cylindrical pipe. The entrance of the cylindrical pipe is right here. And of course, I'm showing a cross-section of the cylinder. And we're going to assume that as the fluid enters the pipe, it's in plug flow. So we have a uniform velocity I call V inlet. So we have plug flow at the entrance, and we have the no-slip condition at the walls of the tube. And therefore, after a certain length, which is what we're after here, after a certain length, we're going to have this fully developed fluid profile. It's the profile that you could fairly easily calculate using the Navier-Stokes equation, fully developed flow. And the question is, what is the length that it takes to get to fully developed flow? And our assumptions are going to be constant density and viscosity. So the assumptions are listed over here. Constant density and viscosity. Those are functions of temperature. So in a sense, I'm assuming constant temperature, but constant density and viscosity, rho and mu. Laminar flow in the tube. Steady state flow, no slip at the walls, and as mentioned before, cylindrical geometry. And again, the question is, what length through the tube does it take to get this fully developed parabolic flow? Well, the actual answer to that is because you approach parabolic flow asymptotically, it would actually take an infinite length of tube to get to truly perfectly parabolic flow. So any description of the entrance length incorporates within it some parameter for a tolerance for fully developed flow. And often it's how, or the percentage approach of the centerline velocity to the centerline velocity for fully developed flow. Now, if you take a look in the literature, you'll see correlations, and the correlations are, for example, as shown here. That's a typical correlation. LE is the entrance length, and it's a dimensionless correlation. So you can go through dimensional analysis and convince yourself that the dimensionless entrance length, so entrance length over the diameter of the tube, is some numerical constant, we'll call it A, times the Reynolds number. You might remember what the Reynolds number is. But the problem is the value of A does depend on some criteria for approaching fully developed flow. Often it's not well stated in a lot of references that give the entrance length correlation. And what we want to do in this problem is develop as best we can a more general correlation where we say the dimensionless entrance length, that's the left-hand side here, the dimensionless entrance length is some function of the Reynolds number and then some criteria for approaching this fully developed parabolic flow. And the criteria is this ratio stated here, the centerline velocity divided by the maximum centerline velocity. And the centerline velocity is the velocity at the center of the tube. And it's going to start off at V inlet. That's the centerline velocity. When we have fully developed parabolic flow, the classic solution, the parabolic solution for fully developed parabolic flow, says that the centerline velocity will be twice the inlet velocity being the average velocity in the tube. So we do know what the maximum centerline velocity is, but the question is then, how do we develop this general correlation? So we have to pick a ratio, centerline velocity divided by the maximum centerline velocity. We know it starts at 0.5. That's at the very entrance of the tube. And we know it goes to 1 at an infinite distance. And so the idea is to use various ratios, for example, maybe 0.8, 0.9, 0.95, 0.98, 0.99, and see if we can develop a general correlation for the entrance length where we have a parameter, which is the centerline velocity divided by the maximum centerline velocity as the criteria for the entrance length. So we can vary that parameter and see how the entrance length varies. And we can also take a look at these correlations in the literature that are given as shown by that first equation. And we can say, okay, the value of A that's given in this correlation corresponds to the centerline velocity divided by the maximum center velocity of a certain number, like 0.95. And so that's the idea of this problem, and we're going to do it by simulating the entrance length in a tube, and we're going to do it with various types of fluids, various flow rates, and try to plot our simulations in various ways and develop a correlation. So in a sense, we're going to do numerical experiments. You might think about doing this numerically. We're going to do it computationally, but essentially using numerical experiments, we can pick various liquids using the physical property database in COMSOL, and we can then use various flow rates and plot our data, and we can repeat that for other types of fluids, that are in the physical property database in COMSOL, and as I say, basically do numerical experiments and try to see if we can determine this correlation. So that's what we're going to do, and that is my little introductory part. And so now we get to the actual use of COMSOL. So I happen to have COMSOL installed on my computer, and you should be looking at my the desktop on my computer. I have COMSOL installed on it. The students in my transport phenomena course at UMBC will probably be using COMSOL on what's called our virtual desktop environment. And it's a virtual desktop environment, so they can be sitting at their own PC, their own notebook computer, and they can run COMSOL. COMSOL will actually be running on a server, but it will sort of look like they're running on their desktop computer. In their case, they simply have to click on COMSOL to get it to work. I probably didn't install things quite as well as I should have, because when I start to see everything properly, all the graphics, I have to start run with the high performance NVIDIA processor. I could probably fix that, but I've got to run with that graphics processor, and then I can see everything beautifully. So start up COMSOL. Notice I'm using COMSOL version 5.2. Students at UMBC are using version 5.1. That might lead to a little compatibility issues. And if you're using version 4, the interface looks very different than this. So this tutorial is really for the newest version of COMSOL, at least the newest version in February 2016, which is version 5.2. So start up COMSOL, and you can see here the initial startup screen. And there's two ways to get started. You can actually start a blank model, and that's okay. It just is a little more work because you have to create everything. It's not hard to do. But for most problems, it's actually easier to use this model wizard, and it just prompts you with questions like, do you want 3D geometry? Is your problem steady state or unsteady state? And what type of physics do you want to use? I'll explain that in a second. And it's a little easier just to respond to those questions and get kind of a start on your model. So we are going to use the model wizard. So we just left click. We just left click once on that. Now this problem, it's fairly obvious. It has an axis of symmetry in it. That center line is an axis of symmetry. So we could actually solve this problem using a 2D axisymmetric coordinate system. In fact, if we were smart, that's what we should do. But it's a little more clear, actually, to solve this problem as a 3D problem in a Cartesian coordinate system. It's just easier to see everything because you see the 3D tube, and you can just visualize what you're doing. So I'm going to solve it as a 3D problem. Again, if I were smart, I would do the two-dimensional axisymmetric problem, in which we have an axis of symmetry. That greatly reduces the memory required and the computation time. And again, I could do that, but I'm going to select 3D geometry just because it's easier to see everything. And if you have limited memory, and the students who are using this virtual desktop environment do have fairly limited memory, only about 2 gigabytes of memory, they can still solve the problem, but they're going to have to use a coarse grid. So it's not ideal, but it is a kind of a good way to get started because you can just see everything. So left click on the 3D geometry, So now I've selected that 3D geometry. And the next thing you can see is select physics. And what I'm going to do is under fluid flow, note fluid flow, and I have single phase flow and laminar flow. I think I mentioned we're going to solve laminar flow. You could actually repeat this whole problem with turbulent flow if you wanted to, but we're going to pick laminar flow. So again, I just left-clicked on it. And it even gives you a little tutorial on what laminar flow is. We don't need to read that right now. But now I'm going to add that to my model. So I just left-click on the Add button after highlighting this laminar flow. So left-click on the Add button, and it added the laminar flow physics to my model, and I could add other types of physics. For example, I could add heat transfer if I wanted to, and if I have heat transfer combined with laminar flow, that would be called a two-physics problem. But I'm just going to have just laminar flow, and that has in it the Navier-Stokes equation, which is what I need. And that's all the physics I'm going to select. So the next thing is to go to the study part. So at the bottom, you can see, again, left-click on study. And it's got some options for the study, but this is it's not time dependent, so don't click on that. It is stationary, so left-click on stationary, and that's the last choice. So I can click on Done, and that's the end of the model wizard. And it's just a way to get started on it. I could have done all this manually, but it's just a kind of a fast way to get started. And so I clicked on Done, and now I've got interface here. I don't know if your interface will look exactly the same. You might not have this Add Material part. So I'm going to make the Add Material window go away, because it may not be present currently on your screen. So notice the little X for close. I'm going to get rid of that. It made my graphics part bigger. I can change the sizes of these windows. One important thing, notice Model Builder. So the left little panel has what's called the node tree. The node tree, and the idea here is to build that node tree, and you can pretty much go from top to bottom, build that node tree, and that contains your whole model. Now the previous version of COMSOL really just had the node tree, and you built your model by just building the node tree. So if you wanted to add something to some location in the node tree, you just right-clicked on it, and it would open up a bunch of choices, and you select something, and it added that at that position in the node tree. And that's the modeling method, or the way to build the model that I'm most used to, because I have a lot more experience with version 4 than version 5. Version 4 has all these menus at the top, so it's a more version 5 has the option of using the menus at the top, which are redundant because you can do everything directly in the node tree. So if you're new to COMSOL, you may actually prefer to use the menus at the top. That's perfectly fine. You can do everything using the menus at the top. I'm just more used to building up the node tree by right-clicking on something and adding it. So it's just your preference. A couple of things, so I'm going to kind of do it both ways in this tutorial. I'll add a couple of things using the menus, but probably most of the things I'm going to do will be using the node tree. So for the node tree, and again, the leftmost panel is the node tree. You start from the top, and probably the first thing you should do, so you can left-click on this first node, and it gives you some options here And it's probably good practice to give your model a title. Currently it's untitled, so I'm going to call this example. And then it's probably a good idea to give a little more of a description what this is. And so this is an example for ENCH 630. That's what I'll call it. And you can give it passwords and author and all sorts of things. That's really all I'm going to do. And in fact, you don't even have to do this. It's kind of optional. So, but it's very easy to get confused if you have a bunch of models, what model does what. So it's nice to put some information in this very top node in the node tree. Okay, but I'm going to now click down to the next node. And it says global definitions. Okay, global definitions. And I can access all of that from the top menu from definitions, but I'm going to just do it the old-fashioned way right now, the way I'm used to. And global definitions are things that are going to apply globally for the whole node tree. So it's possible the node tree will have several different models in it called components here. And you might want to have different definitions of things for different components, different models. I think that might be kind of confusing if you try that. So we're going to have some definitions of things that are going to be global. They apply to this whole node tree. So again, I could access everything with this definitions tab, but I'm going to do it the old way. So what I do is I right-click on global definitions, and then I have the things that I can add. I'm going to start off adding parameters. So I just now left-click on parameters, and now you see I have a new window, which is called parameters. And this is for convenience, but it's good programming practice to give a name to a parameter that may appear in your model so you can conveniently change it. For example, one of the parameters that we are going to change is going to be the inlet velocity for that tube. And I'm going to give it the name V inlet. So just type in V inlet. Okay. And if you read the problem statement, it suggests one value to get started, which was 2 centimeters per second for the inlet flow velocity, or in other words, 0.02 meters per second. So I'm going to put that in, 0.02. And the units are going to be meters per second. So to put in the units, I put in the left square bracket, m divided by s, and then the right square bracket. So that's how you put in units. And now just to see that it's gotten accepted, I can click someplace else. And you can see my expression here is the same as the value. And I could put a description here if I wanted to. Maybe on the first one I will put a description. It's obvious it's the inlet velocity. Okay, inlet velocity. Let's click back over here. Okay, so V inlet is going to be my parameter. I can use that symbolism, V inlet, elsewhere, throughout my model. And in this parameter table, I can just change the parameter, from 0.02 to 0.03. And saves me the trouble of changing the inlet velocity in the rest of the model in case it occurs in several locations and I might forget where it occurs. If I tried to change it manually, so if I put in the number 0.02 meters per second into my model directly, and it might be in there 3 different locations, and now I want to change it to some other value, 0.05 meters per second. I might not be able to find all those locations, and I might get, totally messed up. I might just change 2 out of the 3 locations, and the model will get messed up. So it's good practice to start off with a table of parameters. And so what else do I have? Well, I've got the length of the tube. I may or may not change it, so I'm going to create another parameter called length, L-E-N-G-T-H. And I have a standard practice where I put an underscore somewhere in all my parameters just to make double sure that I'm not accidentally using some variable that's inherent in COMSOL. For example, the coordinates x, y, z are used in COMSOL, and I don't want to use those as parameters because they're already the coordinate system, or t for time. And so to make completely sure that my parameters are not used by COMSOL in some way that I don't know about, I put an underscore somewhere in the name, and if it's not going to be any place else in the name at the end, and that just makes sure that I've got a unique name. So it's really length underscore, and the length of this tube in this problem is 0.1 meters. So it's 0.1 square bracket meter square bracket. And again, click someplace else. You can see didn't make any mistakes. The value is the value I put in there. And we also have radius. So the radius of the tube, and I'm going to use radius, but then underscore, just to make 100% sure it's a unique name. The radius, so the diameter of the tube was 1 centimeter, that's 0.01 meters, so the radius is going to be 0.005 meters. That's the radius. And I could have more, but those are the 3 main ones that will be convenient to use. Now, I should mention that parameter, I can define a parameter that is some algebraic expression of other parameters. Key thing about a parameter is that it's a constant. So I can have another parameter, I'm just going to call it test 1. So I'll use my convention, I'll put an underscore 1. Test 1 is a parameter. It's going to be kind of a fictitious parameter that's I'm only doing this for the sake of illustration. But the parameter test 1 could be length times radius. I'm not even going to use that, but let's say, so length, so it's length underscore times, and times is the asterisk, times radius, asterisk, or underscore. And that's a new parameter that's actually the product of 2 previously defined parameters. That's completely fine. And you can see COMSOL gives me the value of it. I'm not even going to use it, but you can see how you can build up a pretty useful parameter table with some parameters defined to be numbers, other parameters defined to be products of previously defined parameters. And then it makes it easy to use these parameters in your model, and if you really thought about things to change the conditions of your model, you only have to change things in this table, and makes it very convenient. So that's all I want to do for parameters, but I also want to introduce you to variables. So again, variables, I could access it with definitions. And there's probably some other way to do it. These upper menus are very redundant. Yeah, here it is here. So I could also do it right here. You can see my mouse pointer. Variables, but again, I'm going to do it the old-fashioned way. I'm going to right-click and variables. Okay, variables. You might notice it's only going to let me do 1 parameter table, so it's not going to allow me to add another parameter table. But it will allow me to add variables. Now, variables are kind of like parameters, but they are functions of the independent variables. And I'm not really going to use any here, but I'm just going to make an example. I'll call it test 2, since I already used the name test 1. So test 2, and what can the expression be? It can be an expression of the independent variable. So why don't I say it's going to be x times y, and maybe just to kind of show you the algebra here, how do you take something to a power? It's the caret, so x times y squared. Okay, that's a variable. So test 2 is essentially a function, but it's a special function that COMSOL calls a variable, and the independent variables are going to be the independent variables of the problem. So let me click so I will left click on test 2, and you can see it understood what I did and gave me meters squared. And let's do a couple of other things here. So let's say I have an expression, and I'm going to multiply it by something that's not defined, and I'll just make up something. So let's just say ABC. So ABC times x times y squared. Now, COMSOL is not going to know what ABC is unless I accidentally pick something that's an internal variable. And so what is it going to do? And you can see it gave this little orange color, which means COMSOL is confused, but it will keep going. It's kind of risky to keep going. You can hover your mouse over there. It says unknown variable ABC. So it didn't know what ABC is. That kind of gold color, orange gold color, it's kind of like a warning. It'll let you keep going, but it's confused, and you can see why it's confused. It doesn't know what ABC is. So let's get rid of ABC. And again, I'm going to click back on test 2. It's back in black. Black means COMSOL's happy. But let's do something else that will make COMSOL very unhappy, so that it's going to, it would not even allow you to run the model. So let me put in a left parentheses, and then I'm going to put in 2 right parentheses. That is definitely a syntax error. So again, let me left click on text 2. I guess I could also press the enters key to enter that expression. It's not really entered until I do something else. But let me left click on test 2. Now you can see it's red, and that's definitely an error. You can see it's a syntax error. COMSOL will not let you run the model with a syntax error. It will let you run the model with a warning, but obviously there's something wrong, and you should be prepared for some crazy results. You don't want the orange or the red. And here again, I made an obvious mistake. If I get rid of those parentheses, I'm back to something that works. Okay. And the same thing, the variables can also one variable can refer to a previously defined variable. So I can say, test 3, and test 3 can be equal to test 2. That's a variable, in other words, a function of x, y, z, or time, times something else, so maybe times 5. I'm just kind of making things up here because I'm not even going to use those. That's totally for the sake of illustration. Okay. So those are parameters, variables, and the other thing I could show you are functions. I guess I will show you functions. I don't use functions all that much. I do use parameters and variables a lot. Variables are essentially functions, but they are functions of the independent variables of the problem, and you couldn't apply that function to some other types of independent variables. So it's not like an arbitrary function where the functional form is what's important, but you can do that. And so I'm going to right-click, and this time I'm going to put in an analytic function, okay, just to show you what it is. And so analytic function, it's AN1, that stands for the first analytical function. And we have the arguments of the analytical function, which are going to be x, and the expression is also x. So that's a very simple analytical function. The f of x equals x, and obviously I could do something else here. I could add, it's x squared. So the argument is x, and the value of the function is x squared. So it's f of x equals x squared. If you, want to see what it looks like, you can plot it. So I'll hit the plot button. Hope you can see that. And you can see I just plotted my function. And the other thing about units, you can demand that the argument, in other words, the independent variable, must have some units. And when the function spits out the value, it can be with units as well. Whenever I've done that, I've often forgotten what the units are. So now I always have dimensionless functions if I ever use this. And that does mean that if I apply this function to something that has units, like z, I've got to divide that z by the dimensions. So since z has dimensions of length, I'd have to divide by 1 meter. So 1 left square bracket, m right square bracket, to make it dimensionless. Okay, I am going to change this back to x. So I've got this very simple function, f of x equals x. Let's plot it again. And you can see what my function looks like. Not very exciting. But I am going to use this function just to illustrate what this function is. Of course, it really doesn't do anything. It just takes a value of x and puts and just outputs the same value of x. But that is how you define a function. A very common mistake is to think that you put in the function name and put in left parentheses x, right parentheses. That's not the right syntax. If I click someplace else, it's going to say no. That's a big mistake. It doesn't, it just wants the name of the function where it says function name, and you give the expression in the argument elsewhere. Now, when you use that function, you do have to put in the parentheses and what the argument is, because that's why the function is different than the variable. You can apply that function really to anything. The variable that we just saw a little earlier, those are functions, but you cannot change, the x, y, z, and t. That's kind of frozen. You cannot change the arguments at all. That's the difference between a variable and a function. Okay, parameters, variables, functions. You can see we're proceeding down the node tree. Next thing actually is materials, and I'm going to do this a little differently. Well, okay, I'm going to try my hand at this upper menu system here. Like I say, it's a new feature in version 5.2, use menus. I guess people are used to menus. I'm used to the node tree. But add a material. Okay, so we have a physical property database, and I'm going to now add a material. So I just left click on add a material. You can see it opened up a new window. These are materials from the material or the physical property database in COMSOL. And I'm going to add liquid water because we're going to have liquid water flowing through this tube. And therefore, I open up where it says liquids and gases. It's a liquid, so I open up the liquid, I find the water, and you can see the other options here. Some of these we may use for other simulations, ethylene glycol. Notice it has engine oil. That's not really a well-defined liquid. It's got gasoline. That's also not really a well-defined liquid. But a lot of these are well-defined liquids, but we're going to pick water. So I left-click on water, and I'm going to add it to the component. The component is down here. I'm going to add it to the component, and so left-click, and every once in a while it gives me this little error. I just say, OK. It's really a warning. Notice the question mark is a warning. Just say, if you see that, I don't know if you will, just say OK. It seems to be harmless. But notice it added water. It kind of did it down in this component node. And I should notice that the global definitions is a node. Parameters, variables, etc. were subnodes. I can see that by collapsing the global definitions. You can see now I can't even see the subnodes. Open up the subnodes and I can see what they are. It added the material into the component node. And let's look at it a little bit. It's liquid water. And you can see some of the physical properties here. We've got the dynamic viscosity. That's the viscosity divided by density, also called the kinematic viscosity. It's got the speed of sound. We're not going to be using that. Thermal conductivity. The density, actually, we will be using. It's got those properties stored in it. But what exactly are these properties? Well, I can kind of burrow down in the node tree. So underwater, I can open it up, and it's got this basic definitions. Open that up again, and let us find, let's find something here, density, rho. What's the correlation for density? And you can see what it is here. It's actually a piecewise function, but between 273 Kelvin and 553 Kelvin, it's using this function for the density. And if it's cut off here, you can hover the mouse over it and see what it is. And the same for these other things, like heat capacity. We're not going to use heat capacity. I guess one that we are going to use is eta, the kinematic viscosity. So let's click on that. And you can see it uses these two functions in two different temperature ranges. And again, you can see they're functions of temperature. So the physical property database is kind of convenient, because otherwise we have to figure out what the viscosity is or the density. But now we've got this in there, so we don't have to worry about it. If we need any physical properties, we've got them already entered. So collapse that again. And the final thing I want to show you in part one is building a geometry. That's the final thing. So we have to make a tube, because we're going to have flow in a cylindrical tube. So again, I could do all this in these upper menus. So I could probably, yeah, here's geometry right here. I have no doubt. Let me click on geometry, and you can see explicitly some of these subnodes here. You know, I think for a new user, these upper menus are probably worth using, but I'm kind of an old timer here. I just like doing things directly from the node. So if I right-click on geometry, I'm just going to see all these options, but that's the way I'm used to it. And I'm going to select cylinder. So select cylinder, and so it's selecting this geometric shape cylinder. In fact, to actually see it in my window, I'm going to make this graphics window a little bigger. I don't need this material window anymore. So notice, close the material window, make the graphics window a little bigger. I've got default values in here, which are not what I want. But just to show you the cylinder, I can left-click where it says Build Selected. It means build what you've selected, which is the cylinder. Here's my cylinder. It's not the right geometry, So I'm going to change the geometry. And the radius of the cylinder, remember we had this parameter called radius with an underscore. It's the value of 0.005 meters. I can use that. And the height is length, L-E-N-G-T-H with an underscore. Those are parameters that I defined. And so now we can build the cylinder that we actually are going to use. So let me click on Build Selected. See, it's a little tiny thing there. Can't even see it. But we can kind of resize it. So if you go to this button, it looks like a three-dimensional grid. Notice we're doing everything in the Cartesian coordinate system, X, Y, Z. But click on this default view, and you'll see our cylinder. A little bit about the controls here. If you left-click and drag the mouse, you can see you're rotating the cylinder. And simultaneously, you can see we're rotating the coordinate axis. So left-click and drag the mouse. In other words, you hold the mouse down. You're rotating. And by looping around, you can, rotate this thing in any orientation you want. Notice I've completely reversed the coordinate system. But right-click and drag the mouse. So hold down the left click and drag the mouse. You move it axially, or vertically in the X or Y direction. And to make it bigger or smaller, you can either zoom out or zoom in. So let me zoom in, and we can see, zoomed in view and etc. So by using the mouse, you can see your cylinder quite well. If you get things kind of all fouled up, you can go back to the default view and take a look at your object. Notice I do have the position of the cylinder is located by the center of one of the faces, and that's going to be located at 0, 0, 0. That's going to be the center of one of my faces. I could change that. That changes the location of the cylinder in the coordinate system, but it's okay to leave it as it is. So my cylinder, the center of one face is at 0, 0, 0, and the radius is this parameter I called radius, and the height is the parameter I called height. Notice one more node that we're not even using. It says form union. That's a default node, and we're really not even using it. It's just that if we had several objects here, by default, COMSOL would say take the union of all those objects. And you could also change that. You could actually, subtract one object from the other, and the difference in those two objects would be the object you want. You can do all that from geometry, and don't have time to explore it, but it's also up here. You can do Boolean operations. Let's take a look at the Boolean operations. So I can take two objects, I can fuse them together, and I've got the union of those two. I can take the intersection, the difference, and I can kind of build up fairly complicated geometric shapes. It's not quite as good as AutoCAD or something like that, but with a little bit of effort, I can build up, very complicated or pretty complicated shapes. I should mention you can also import into COMSOL shapes that are created by some of these other 3D modeling software like AutoCAD, if you have access to those. But if you don't, you still can build up a fairly complicated geometric object just by simple, spheres, cones, you can see them here, helix, etc. And then taking unions or differences, and if you're kind of artistic and inventive, you can create, pretty impressive geometries. However, we just have a cylinder. Okay, so that's going to be the end of my part one of my tutorial. So I'm going to minimize the screen here, and I'm going to stop sharing, and then I am going to stop the recording, and this will be the end of part one. So stop the recording. So thanks a lot for viewing part one, and I'll meet you on the other side, and we can see part two. So stop the recording. Stop recording.